All right, well, welcome everyone, and thanks for joining us today. We're going to go over the most recent update on the work we've been doing on a wind miles model service under the guise of demand prediction improvements for integration of tactical departure scheduling and traffic flow management. But really, we see this as connecting very significantly with the work that NASA's doing right now in the digital information platform, and hopefully this is a good connection with those types of activities. Obviously, also connected to ATD2 in terms of the concepts of the TOS and some of the concepts, capabilities that have been developed for using the TOS and ATD2. But just as a review, the objectives of the effort, we really split it up into two different objectives. We're about halfway through the effort at this point, so we're coming to completion of technical objective 1, and then we'll be turning our focus a little bit more to technical objective number 2, although there are definitely still some things that we want to improve and enhance with the wind miles model itself. So the first objective is to develop and operate a wind miles model as a data service in the cloud. And I think it's important that we recognize that a lot of the types of projects that are done under SBIRs and NRA contracts and things like that are often to develop a prototype or do a piece of research and develop a report and deliver that report. Whereas in this case, the objective really is to not just develop, but to operate also, to operate 24/7, 365, to have something that's out there as a service that is an example, a prototype, a model that potentially could be followed for other types of services that provide different types of capabilities to support the NAS users, air traffic service providers, et cetera. So we'll talk about that as we go through, and the fact that this is in operation now and is available out on the web. We can handle a number of different input models for various use cases, as you'll see as we go through the demonstration. And one of the things we've been working on most recently is the self-scoring mechanism. We'll talk about that. Still a little bit of work to go on the self-scoring mechanism, but we're making really good progress there, and I'll give you an update of where we stand. And then the step following, the second technical objective, is to use that self-scoring mechanism and use the information that we have about the wind forecast and observed wind data to be able to develop and operate a wind nowcast model. The intent being to create something that is much more dynamic, that is updated more frequently than some of the current wind models that exist, to be able to fill the need for things like near-term flight planning and decision making and predictions in the near term, so that we don't have that lag that exists with some of the existing wind models. And also looking at lower altitudes to be able to prepare this for the kinds of things that are going to be needed by new entrants. So referring back to the ATD2 TOS use case, this is one of the things that in the ATD2 experiments, that there was a desire to have not just a ground distance of the proposed route, but also look at the effective air miles, so that wind could be considered in terms of the benefit or comparison of one potential route versus another. So what we've done is developed that capability, a wind miles model, a wind miles service, as a web service online. And the simple idea is that we're correcting for the wind component to be able to come up with the effective wind miles. This is done on a segment by segment basis, and then we add that up over the segments to get a total wind miles. This display here will show you more detail on this during the demonstration, but the important thing to understand here is that this is really just a status web page. It is not the service itself, if you will. this web page can send requests to the service so that it can be used for demonstration and experimentation and one-off type of requests for wind miles. But the real service itself doesn't operate with a user interface, but it's just a data interface and API, so that any users, airlines, ANSPs, whatever, can automate the process of using this service and requesting a wind miles calculation. But this web page also does provide a status for the service, indicates, first of all, if it's online or not, what the recent forecast times are, and then this is the self-scoring mechanism where we are measuring the accuracy of the wind forecasts by comparing the forecast data to observed winds and giving measurements in near, medium, far, and overall time frames. I'll admit that this data that we have here is mocked up right now as we're fine-tuning some of the results and model training. We've got some pretty detailed and interesting work going on in the background with some ARIMA time series models that we're training there, and we are close to having that out there, but just a few ends that we're tightening up. We can provide opportunities for the queries, the requests, to have either just a departure airport and arrival airport at a time, or full flight plan route, including optionally departure or arrival runways. And then the service requires an aircraft type, a filed altitude, and a filed speed. And then after calculating, here's the result, for example. So the ground distance from LAX to Dulles would be 2,000 miles, but on this particular time frame when this was taken, the wind miles would shave about 300 miles off of that. The effective flight distance is 1752. So that's, again, just an overview of what this is. We'll go through a more detailed demonstration here toward the end, but let me give you a little bit of under the hood discussion of what is actually going on. So we have the overall wind mile service, and this is kind of an interesting discussion point. The wind mile service itself interacts with other services that we have created to support this, and the interesting thing is that these other services could also stand alone as exposed web services with APIs that can provide the same type of interaction mechanism for any user that would be interested in those. So we have the trajectory modeler service, which actually is taking a horizontal route and altitude and speed constraints and turning it into a full four-dimensional trajectory. We have our clearable routes network implementation, and this is used if the user just sends in an origin and destination. We use the clearable routes network to generate the most likely the expected route that would be assigned given ATC procedures and ATC preferred routes, so that we can get the best prediction possible. And then this sector crossing service that we're continuing to work on is essentially, you can think of this as a machine learning approach to generating a new form of adaptation data. The letters of agreement, the standard operating procedures, some of them are encoded in ERAM adaptation data. Some of them are in the published charts for stars and departure procedures. But what we're doing here is a machine learning approach to generate that adaptation data, so we don't have to have a manual process of extracting that data from the adaptation. And then, of course, there's the wind service itself, where we are accessing the RAP forecast data and then bringing that down and formatting it to be able to be usable in the trajectory modeler service. We've deployed this now out to an operational environment in AWS. We have 4 different environments, if you will: a production environment, a staging environment, an analysis environment, and then our development environment, which is not an AWS, but is on internal virtualized servers. But in AWS, we have the ability to both run staging, to be able to prepare for switchover, and then be able to push things into production. We've got an elastic load balancer to be able to handle requests that come in. And we also now have stood up an analysis environment where we're able to do playback for analysis purposes, to be able to look back at previous events and compare our wind miles to wind miles data from other sources. And I'll describe that in a little bit. We also have monitoring of the production system using Zabbix that's out there. We've got a dashboard that we can pull up on demand, and this is also automated so that any of the problems that occur with the system provide an automatic notification to our support monitoring staff that are watching for any of our production systems to go down, so that can be remediated quickly. So let me just get into a little bit of both the self-scoring mechanism as well as the initial test results. Are there any questions before I do about the deployment or anything we talked about so far? Okay, great. Feel free to interrupt if there are any questions that come up. So first of all, before we talk about the self-scoring mechanism and the test results, let me just describe the forecast data source that we're using. I think that many of you are familiar with the NOAA rapid refresh data. So this is gridded winds aloft forecasts at 25 millibar levels, 13-kilometer grid, hourly forecasts out to 52 hours for some of the model runs, or 22 hours for each hourly run. But as we referred to earlier, there is a delay in terms of the availability of that run, so that it's less up to date for very near term trajectory modeling and prediction efforts. That's part of what we want to address in the second objective of this effort. But let me first talk about the initial test results. So we were able to obtain historical flight planning data from American Airlines. They were kind enough to provide us with a large set of data from which we extracted 340 flights over 5 random days. And we were able to use our analysis environment that I referred to on one of the previous slides to be able to run a comparison of the wind miles as computed by our service versus the wind miles as computed by American Airlines flight planning system. Now, let me show you first on the left side here. Actually, this is the histogram of the differences. I'm sorry that these aren't labeled, but this is the number of occurrences on the vertical axis and the number of nautical miles of difference on the horizontal axis between the filed ground distance. So this is using the filed route and comparing the ground miles. In other words, wind is not affecting this left-hand chart. So we see that even without using the wind and trying to predict the air miles, just trying to use the adaptation data and the flight planning on the same filed route of flight, we actually have a relatively significant difference between the American Airlines data and our data. Now, as we all know from working in the area of air traffic automation systems, there's lots of reasons for this. There's details of what's being done in the terminal area after you get to the end of a star, or as you transition to a departure procedure or something like that. There's problems with the timing of the adaptation data and changes in procedures, changes in locations or adaptation of fixes and all that kind of stuff. So this is one of the things that we're digging into right now to be able to identify, what the source is of these differences just in the filed ground distance. The right side chart shows the difference in the computed air miles. So this is where we're actually getting the output of the service, where we're using the forecast wind data, and we are applying that on a segment by segment basis to be able to calculate the effective wind miles using the flight plan route still, but looking at the effect of wind. The thing that I find, very interesting here is that the horizontal axis is on the same scale on both of these charts. And yes, the difference in the air miles is certainly a wider distribution. There's more differences indicated here, a greater degree of difference indicated here in the air miles and in the filed ground miles. But if we were to remove the distribution, the uncertainty, the deviations associated with the ground distance, which we should be able to improve this since we expect it's just based on adaptation errors and things like that, we can expect to see the air miles calculation become even tighter. In other words, the ground miles difference seems to be a large portion of the contributing to a large portion of the difference here that we see in the air miles. So as you can see that, we're doing well in terms of not being biased. We've got a standard deviation maybe of 50 nautical miles or something like that. I think there's the details in the report. So, still a good opportunity for improvement here. But, definitely within the ballpark for initial test results, which can now guide our continued improvement of the accuracy.
Hey, Chris, can I have a question?
Yeah, please.
This is Ian. Hey, how are you?
Good.
Yes, good. So air mile, so what time does this air mile get predicted? Is it American Airlines, for example, when they kind of push back or take off? Or do you know when this prediction was made?
Yeah, great question. And we got that information from American Airlines. And our understanding is that they're doing their flight planning process and generating this about 4 hours before wheels up time. So, there is a relatively significant, gap there in terms of the forecast data that's going to be used for these predictions. When we ran our analysis, and actually, Jason, maybe you can help me out here. I think that we aligned our data to be at around the same time, so we were comparing that. Is that right, Jason?
Yeah, that's right.
Yeah. So we used the same forecast issue time that would effectively match what we think the American Airlines forecast issue time would be that they were using. Now, that being said, they use a completely different wind forecast product. We're using the NOAA RAP data. They use a global data source that they have access to. So there are definitely going to be differences just for that reason alone.
So do you know if that is only air mile prediction by American Airlines, like 4 hours prior to their scheduled departure time, or do they have sort of follow-up updates? If pushback gets delayed or takeoff gets delayed, I wonder how they kind of wanted to update their air mile. It's 4 hours. It seems to be very, very long.
Yeah, and that's a great question. I do not know if they do any updates to it, but I think that's a perfect question to kind of talk about the benefit of having a service like this. My impression is that the calculation of air miles is something that's integral to their overall flight planning process, which is a larger and more significant effort that they're engaged in, and that they may not, I don't know for sure, but they may not update the air miles prediction at pushback, for example, just because it's a more involved process to deal with updating the overall flight plan. Whereas if there was a service with a simple API that they could just hit to be able to get that update, there would probably be more opportunities for them to do that and improve their operations as a result.
Thanks, that makes sense.
Yeah, good question.
I have a quick question on this slide. The horizontal axis, the negative values, can you define the horizontal axis? Maybe you did and I missed it, but when you see a negative value, does that mean that you're predicting less or more than American Airlines?
Yeah, that's a good question. And I probably, I've got a 50-50 opportunity there for guessing, but I wouldn't want to, make that guess and be inaccurate. So, Jeremy, I can get back to you on that, but certainly you're absolutely right that it's in the negative case, one's higher than the other. Jason, do you happen to know the answer? Yeah. Yeah. Jeremy, we'll check on that and figure that out.
Okay. Yeah. I mean, the reason I'm asking is because to my eye, if I compare these two distributions, it looks like the air miles one has shifted some of the, like there's mainly a shift going on to the left.
Yeah.
And so then that makes me wonder, does that mean you guys are being too aggressive or too conservative? So that's kind of where the question is coming from.
Yeah, that's a great question. That's a great question. All right, we'll follow up on that. All right, a little bit about the self-scoring, and then we'll jump into the demo. The idea is to be able, as you saw when we showed the sample of the page, is to be able to allow users of the service to understand how accurate the service is at any given time. Our plan is to have the overall self-score service like you see on the web page, but then also when we return a query with a calculated wind miles, we'll also have a dynamic estimate of what we think the accuracy is, so we can provide some confidence intervals with each of the responses that's sent. So we're doing the self-scoring metric by comparing observed wind data to forecast data, and then smoothing to be able to handle cases where we don't have observed data. And quickly to review on the different sources of observed wind data, the first one is the MATIS aircraft-based observation, which is flights that are equipped and sending over ACARS or some other communication mechanism their airborne measurement of the wind. And that's available in real time for the operation of the system. We have that data coming in to the system to be able to feed the observations. That's all implemented, and we're collecting that data. And then the other observational wind data source is a satellite-derived high-density winds that operates off of satellite imagery that is able to both detect clouds or other visible moisture in the atmosphere. It's able to predict and understand what the altitude is of that visible moisture, and then use the tracking of the movement of that to be able to get an estimate of the actual winds. And so we're able to use both of these observed data sources and then be able to match those up with the forecast data from RAP. And so this is just a chart that shows kind of a combined example of the derived wind motions data as well as the Mattis data. And you can kind of see that some of the data is grouped in blobs, if you will, right? And so that's where there is visible moisture, and we're getting that from the motion-derived winds from the satellite data. And then you can see there are others that are more linear in nature, and those are observations that we're getting from a flight that is equipped and is reporting data and is flowing through those areas. You can also see, kind of the differences in accuracy. Good accuracy over the landmass down here to the south, poor accuracy over the coastal regions and up here to the north. So it's kind of interesting just to get a feel for what the different accuracy levels are. So we're rolling all of this up into an overall accuracy metric, like you saw on the chart here at the beginning. And in fact, Jason, maybe now's a good time to switch over to the demonstration. But those accuracy individual comparisons of the observed wind versus the forecast wind are then being combined using a time-lagged filter to be able to create these estimates here of the overall data. So we're weighting the most recent observed data more than older historical data with an exponential smoothing. Any questions before we jump into a quick demonstration? All right. Jason, I'm going to make you the presenter, and you can take it away.
All right. Open up my sleeve. Okay, so here is our current running live system that anyone can get to over the internet. We're doing it at services.mosaicatm.com, flight wind miles web. We can share this with anybody if they want to email me. So yeah, as Chris was saying, this is just the front end. Everything's interesting is really more in the web services side. I think a lot of you guys have seen the open API specification. We've been using on ATD2 as well. But our wind miles primarily supports these web services. So we have 4 different kinds of requests. This one is where you give it the route positions and enough of the aircraft information to model the trajectory. That was kind of the idea of what we thought might get used by like a TOS service. There's a 4D trajectory request where you just pass in all the latitude, longitude, altitudes, and it does the math on the winds. And then the 2 on the web front end, I'll show you. We have 2 different kinds of web service requests. One is, as Chris was saying, you just give it the airports and aircraft type and speed and altitude, and it will use our cleared routes network to determine a 2D trajectory, which we then model and compute the winds. And then here's our most common type of flight plan request, called the route flight plan request. Here's where you get the your field 10 flight route string, and optionally you can also get the airport runways to model the SIDS and stars better. So let's go through and do a live demo. Up at the top, we have current, most recently loaded RAP forecast. They come in a little bit late. Right now we're using the 1400 winds forecast, and we can predict wind miles all the way out till the 15th, 1300. The RAP forecast product, I think it's every 6 hours you get a 52-hour forecast, and all the remaining hours you get a 22-hour forecast. And here's our new display of the RAP accuracy. These are, as Chris was saying, these are all kind of notional values. We're integrated with an application computing the accuracy. However, we're still working on a couple kinks on the values it's generating. The idea is that these are 95% confidence intervals on the speed and heading, and we kind of break down the forecast into different time periods. A near term, maybe I think that's 0 to 6 hours, medium like 6 to 18, then FAR is 18. It's a 52-hour forecast, and then the overall. So let's jump in here and throw in some data. Let's see some airports dear to you guys' hearts. Let's see, we got 738. Let's go to DFW. Pick a time anywhere in this period. It should be covered. Let's do tomorrow, 2 p.m. And the speed. So speed, altitude, aircraft type, those are used in our trajectory model. So I just did an airport request. So this is going to use the CRN to determine a route between these two airports that was derived from historical route network data. Okay, so we got our ground miles, which is just the two-dimensional summed up, and then wind miles where you plug in the wind, and going west to east. This is good. Wind miles are less than the ground miles generally. That's the case. I can go the other way, and you would hope that it would be the other way around. So ground distance is the same. Actually, it's probably a little different. Do the route picked by the route network, and then wind miles are now more than the ground distance. That's good. We come in here and we can plug in a little cheat sheet. We can pick a real two-dimensional route and see what that does. Okay, and a little bit more fun, I can throw in some runways. See if that makes any difference. So I got 1297. Voila, a little bit more distance there when you play the full flight plan. Yeah, so I guess that's pretty much all there is to the show. The interesting piece is the web service, web services on the back end, and right now we would have to give you, if anyone wants to use it, we can give you an API key that you include in your web service requests. But that would be no problem. Yeah, any questions, or anyone got any other airports they want to try?
I have maybe just a comment, which is eventually in a lot of our use cases for this type of thing, we would probably convert everything to minutes. Is it possible to have the option to kind of convert to minutes so that it doesn't introduce the opportunity for, you know, the user to make that mistake on their own, or like make a mistake trying to do that conversion?
Minutes.
Like flight time.
ETE. Yeah. Yeah, definitely. Yep.
Yeah, I mean, we can give the ETE. It's just on the wind miles, I guess. The ETE is the same.
That's interesting. Yeah. So when we do the trajectory calculation, from a single trajectory, we can calculate the ground miles and the wind miles. But I think what you're thinking, Jason, is the fact that we don't have a trajectory at zero wind. And so the difference, you'd have to do an additional trajectory calculation with a zero wind field to be able to do that.
Right. Okay.
And Jeremy, do you think that would be useful to have that difference in terms of the ETE with the wind considered versus no wind?
Yeah, because I think when we do our TOS use case, that is the real factor that we care about, is the additional flight time. Yeah,
that's interesting. I mean, I think there's the aspect in the TOS use case of comparing the route option 1 versus route option 2 in the context of the effective air miles. Maybe said a different way. If you had two different route options and the improvement in one of those route options in terms of time was more, right, as compared to the no wind case or the with wind case, that route option has a greater reduction. That might be interesting, but I still think that you wouldn't choose that one if the end air miles would be, or ETE were to be more than another option, even if that other option didn't end up having as much difference between the no wind and the wind ETEs. Do you see what I'm saying? Do you agree?
I'm not sure I followed along there, but I guess from our perspective, like right now you have wind miles 1403.98, but ultimately we want a flight time.
Right.
And because the reason being, right, is that if we get you off the surface 10 minutes earlier, then I need to compare flight times of, you know, toss options to the filed route flight time.
Yep.
And so now if I get you off the surface 10 minutes early, but I'm flying into like a pure headwind, then the flight time will be much higher, which, you know, the trade-off doesn't make as much sense at that point in time.
Yeah. Yeah. That makes sense. That makes sense.
I think that's more just the trajectory model and using the wind impact on the trajectory result, which we can do.
Yeah.
Yeah. Yeah. I mean,
I mean, what happens if you take what is this like if I were to just do this on the back of the envelope, I would just take the filed speed and divide by your two estimates of distance. And then I would say, like, for example, if you go back to the last example you were looking at where the wind miles was longer, that the wind was adding, you know, whatever the difference is here. So it's like 100 nautical miles, divide that by 450, and then, you know, that would be a back of the envelope estimate of how much time the wind was adding. I don't know if that's you know, valid or not, but
no,
ultimately I think we
yeah.
want, you know, the wind adjusted flight time.
Yep. Yep. I think that that's definitely valid as a back of the envelope, and definitely we could add the information here about the wind miles as well as the wind adjusted ETE. You know, I think that because of the fact that it's wind adjusted, I think that it ends up giving the same information in terms of comparison and ranking. That, in other words, you shouldn't ever expect a route that has a higher wind miles to have a lower ETE, right? They should be perfectly correlated with each other. But I also agree with you that, just from my perspective, thinking about it in terms of time just makes more sense. And so I think that we can provide both the wind miles as well as the wind adjusted ETE, so that you know, whoever's looking at it can choose whichever one is most beneficial for them.
Yep. No, I think that would be, I think, useful from our end. And again, I think we could probably do this on our side, but to just kind of reduce the risk of the user making a boneheaded error, you know, it's nice to kind of have it embedded.
Yeah, absolutely. Absolutely. That makes total sense. Good comment.
Mm-hmm.
So I think that's everything. Jason, thank you for doing that that demo. And at this point, just want to open up and see if there are other questions or comments or things to discuss. I see perfect timing. Wes is arriving right now, just as we're finishing up. So Wes, welcome. We appreciate you joining. And we are just doing questions here, but we also have recorded the session so that we'll be able to provide it for replay afterwards.
Great, thank you.
Yep. Any questions from from anyone on what we've presented here today? All right. So our next steps are to continue to enhance the self-scoring mechanism that we've talked about, and we'll send out information when we have this wind forecast accuracy mechanism in the actual web page updated with real data so that you can see the results of that. And then the other thing I'll just mention in terms of next steps is as we start to look toward both the flight-specific scoring mechanism and accuracy analysis, as well as we look at the wind nowcasting, the more kind of real-time, near-term model of wind updates. Some of what we're digging into is some pretty interesting algorithmic approaches to do machine learning on the observed data that we have, and then learning how to extrapolate that to areas that are not covered by the observational data, but potentially taking into account in that machine learning other data sources that we do have that we expect will have correlation with the wind data. So, for example, surface pressure is one of the things that we all know can provide some correlation with wind in a interesting and complex way. So the machine learning that will be involved here is going to be pretty interesting because there's spatial factors, there's time factors, there's conversion, if you will, of impacts from pressure to wind and stuff like that. So pretty interesting effort that we're going to be looking in on there, and look forward to reporting out the results as we move forward on that. So, but with that, we will close this up. Thanks everyone for joining, and feel free to send any other questions or thoughts separately as they arise.